Hey everyone, welcome to lesson 4C. So this is our third out of 4 lessons for this unit. Like I said, it's a pretty short one. So today we're going to be talking about static equilibrium. Alrighty, so the first thing I want us to do is I want us to think through this problem. A diving board is held by supports. I have this support A over here, the support B over here, then I have this weird little person on the end of the diving board. And this question is just asking us to think through, like, what are the forces happening? So the person standing here, they're gonna have some kind of downwards weight. That is the force. I'm gonna clear all my little drawings there and just focus on the force arrow. So there's the weight of this person. Do you think the force at support A would be down, up? What about at support B? Would that be down or up? And then what do we think about their magnitude? So take a second, read this through. You could even pause the video. I think probably about 2 of you will actually do that, but maybe all of you will. And just try to think through it. What do you think is going on here? Would there be like an upward support here, an upward support here? Would they both be downwards? Would one be up, one be down? What do we think? All right, we're going to come back to this one at the end of the lesson after we've talked about static equilibrium, but that's just kind of our starting point for today. So let's get into some definitions. So statics is this whole field of study. It's the study of forces acting on and within equilibrium structures. And we're going to really get into what we mean by equilibrium today. So while objects at equilibrium could be at rest or moving at some kind of constant velocity, and remember those two things were also very related to balanced forces. For today, we're going to specifically focus on things at rest. It could be viewed as a boring field of study, or it could be viewed as a really necessary and interesting field of study. The fact that you are in a building right now, the fact that you can be in structures that don't just fall down, the fact that you can go to a doctor and have them understand how your body works, all of those things, civil engineers, architects, doctors, and so much more, they require this study of statics and this concept of equilibrium. So there are going to be 2 conditions for equilibrium. The first one is the sum of your forces must be 0. We're pretty comfy with this one. This is our law of balanced forces. Law of balanced forces. And for this one, use your normal sign convention for force. Use force sign convention like the one we talked about in the last unit. So up is positive, down is negative, right is positive, left is negative. Use that normal sign convention. That's our starting place for equilibrium. We're going to add another one in a second, but let's start with an example here. Calculate the tensions FA and FB in the 2 cords that are connected to the vertical cord supporting the 196 kilogram chandelier. Okay, so what we have here is we have this point in the middle. I have FB solely in the right direction, FA up at an angle, and then I have this weight hanging down, okay? I'm going to go ahead and call this weight FC. And they actually already calculated it for us, so FC represents the weight of the chandelier, so mass times gravity. They gave us the math was 196 kilograms. Multiply that by acceleration due to gravity. That's going to give us that 1,960 Newton force. And remember, weight is force. Not all forces are weights, but all weights are forces. Okay, so we're going to start by just applying our balanced force law. Some of the forces should be 0 in all directions. So let's start in the x direction. When I balance my forces in the x direction, I have positive FB, right? That's in the right direction. And then what's going on here, I'm going to zoom in a little bit, is I can split this FA up into 2 different components, an X component and a Y component. Something that they're showing us down here is that we know this angle. If they're telling us this angle up here is 60 degrees, I know that's going to be the same as this angle down there. So I can actually use that to calculate FAX. To find what FAX would be, I would take FA, I would multiply it by cosine 60. So remember, that's just review. You've done that with forces, you've done that with vectors. It's coming back. So I would say minus FA cosine theta. For right now, I'm just leaving things in variables. The only piece of info that I actually know in this equation then is theta. I know that that's 60. I can't really do anything else with that. So let's pause and let's take a look at summing the forces in the y direction. So if I do that, I see that I have this FAY component, so that would be FA sine theta, and then I have this weight component over here, or FC, so minus FC, and I want those to balance, I want those to be 0. And for a problem like this with a chandelier, you definitely want equilibrium. You don't want this thing shaking, you don't want this thing rocking, moving, falling, anything like that. Okay, so here I could actually go ahead and solve, right? I don't know what FA is, that's okay, but I know that theta is 60, and we already said that FC was the weight of the chandelier, so that was 1960 newtons. That equals 0. That means that FA is going to be 1,960 newtons divided by sine 60. You can go ahead and plug that into your calculator, or you can just wait 3 more seconds. We're going to get something around 2,260 newtons. That is FA. Okay, so we've solved 1/2 of this problem. Now that I know what FA is, I can take that and I can go ahead and plug it in over here and solve for FB. So going back to the sum of the forces in the x direction, I'm trying to find FB. I now know that FA is 2,260 newtons times cosine 60. That's going to equal 0. Plug that into your calculator, do a little rearranging. We're going to end up getting FB is 1,130 newtons. And you can go ahead and pause and double check. Are those correct? Plug it into your own calculators. But I have FA and FB. Those are our 2 answers here. So something I just want us to pause and consider is why would FA need to be larger than FB? So if we kind of think about what's happening over here, FA is split into 2 components. In order to for sure balance in both directions, it's going to have to be a little bit bigger. And if you're using the same chord for both A and B, make sure that it's strong enough to support FA because that's your greater force. If you choose a chord that's only going to be big enough to support FB, well, then you're going to have some issues with FA, with that force vector, and this thing is probably going to break at some point. Okay, so the one at the angle should be a little bit larger than the ones that are purely horizontal or vertical. Good work. We're going to keep moving along. Okay, so we know that our first condition for equilibrium is the sum of the forces equals 0. In all directions, apply typical sign convention. Remember, I mean the sign convention from Unit 3. But then our next one is the sum of the torques equals 0. Wow, crazy, wild. This is so exciting, right? So equilibrium, everything should add to equal 0. But we can do a lot of cool stuff within that. And like I said, this is a super applicable field. Something that I'll note here is that your choice of axis, like axis of rotation, or fulcrum is arbitrary. So hopefully that seems a little bit familiar. Like yesterday's lab, I know I had conversations with every single group. It took us a little bit to understand the fulcrum part and what exactly I meant by that, right? I was giving each of you an arbitrary fulcrum, and hopefully what we were finding in the lab is that no matter where your starting point is, all of you ended up having different R values, but we should get the same result, that your torques are still always going to balance out. Okay, so you get to choose where you want to put your fulcrum based on the problem, which kind of helps us out a lot. So we're going to start with a bit of a familiar example here. We have a seesaw. I still want to see if we can build one of these next week, but I don't know if we have a board long enough. Child A has a mass of 30 kilograms and sits 2.5 meters from the pivot point. Pivot point is right there. At what distance x from the pivot must child B, mass of 25 kilograms, place herself to balance the seesaw? So anytime you're dealing with a problem like this, you can think of summing your forces. For this problem, if I sum my forces in the y direction, I want them to equal 0. Let's just take a second and think about what forces are at play here. I'm going to use a different color so we can see it. So I'm going to have some kind of force over here, the weight of child B. I'm going to have some kind of force over here, the weight of child A. I'm going to also actually have the weight of the board itself. Weight of the board. If all of my forces are pointing downwards, I must have some kind of downwards acceleration. We know that's not the case here. Seesaws don't tend to just sink into the earth. I must have some kind of support force. We could call it F support or FP because it's at point P. So when you were to sum all of these, we would end up getting FP minus, let me see, what did I call this over here? FA FB. So FP minus FA, right? That one's going downwards. Minus FB, that one's also going downwards, minus the weight of the board. Those are all going to equal 0. So there will be some problems that require you to do this step to actually go ahead and calculate some things. For this one, we're not going to get super far because I don't have enough info to solve anything there. So let's just try out summing in our torques. Sum of the torque should equal 0. And then here's where we want to be a little bit careful. Where would you want to choose your fulcrum to be? For these seesaw problems or the lab balance problems, we can probably say we want to choose point P. I would agree with you, think that's a great idea. We should definitely choose point P. When I choose point P, so when I calculate at P, that's going to cancel out the torques produced by FP and W. So those FP and W torques, they're going to go to 0 because my R value for both of those would just be 0. So what I'm left with is 2 torques. The torque produced by child A over here, would that one be positive or negative? So he has a weight, he would be pulling down, we would kind of go down and around. That's going to be counterclockwise, so positive. So I can say positive RAFA. And then the force of child B, well, that's going to go down and it's going to want to bring this thing around. That's clockwise, so minus RB FB, and that's going to equal 0. We can go ahead and plug stuff in now. So RA was 2.5 meters. What actually is FA? So if the child's mass is 30 kilograms, well, FA would be 30 kilograms times 10 meters per second squared, right? This force is just the weight of the child, so 300 newtons. RB, I don't know what that is. That's what I'm solving for. The force of this other child would be 25 times 10, or 250 newtons. That's going to be equal to 0. We can rearrange a little bit. I'm going to get 750 newton meters minus 250 newtons, and then just x. That x is going to have a unit of meters. That equals 0. 750 equals 250x. X is going to end up being 3 meters. And that would be our final answer. So the lighter child would have to sit a little bit farther away to kind of compensate and balance out in this case.